Well, hello, and welcome to today's webinar. We're going to discuss basic standalone PV system sizing. We did this webinar before a few months ago, but it was so popular and there's so much demand that we decided to do it again. For those of you who may have attended last time, it will be similar, but we have made some adjustments to it. SunWize now has an online sizing tool, and we're going to cover that as well. So there have been a few things we've tweaked to it. So if you're repeating this one again, you're going to pick up a few more things. So it's nice if you join us again for this one. If you haven't, this is your first time. Thanks for joining us. Just to go to a little background, my name is Rob Rallo. I'm a senior engineer at SunWize, and I have over 25 years experience in the off-grid solar business. SunWize has been around for over 20 plus years in the off-grid solar business. They do everything from standalone systems, PV, battery backups, as well as component sales. SunWize has offices in various places around the United States, with warehouses on both the West Coast and East Coast, and the headquarters is in Oregon. As I mentioned, we are a provider of standalone systems, hybrid systems. We also do cycle charge, battery backup. We do pre-assembly and QC testing of those. We also can produce them in ISO 9001 certified facilities, and when needed, we can also do UL 508A. Our systems are designed IEEE as well as NEC, and we can also provide components as well. And we also provide various services. We can help you with technical writing, specifications, design, training, troubleshooting, things like that. So with that being said, let's dive right into today's topic. And again, this is basic standalone PV system sizing. So what that means is this is just kind of a back of an envelope. It's an estimate or a ballpark, okay, because we're going to do this all manually by hand. So if you were to use a computer, you can get it more accurate, but this will at least get you close enough. Let's call it plus or minus 10% or so, okay? If we have time at the end, and again, we're going to try to keep it simple. If we have time at the end, we'll dive into a few more complicated things like battery derates for temperature and aging, the effects of MPPT chargers and how you would use that in the calculations, 60-cell modules, and also low probability. And again, that's if we have time at the end. We'll see. Okay, so just to give you a brief overview, we're going to start with initial considerations. We're going to go into the sizing methodology. Then we're going to cover the system performance and losses that have to be calculated. Then the load calculations. Then we're going to actually get into the sizing of the solar array, the battery. Then we'll run through a few examples with you. And new this time around is going to be our design tool. And when Errol and I went ahead and updated this presentation to add that in there, we were fascinated actually at how well that tool worked and how it lined up with these manual calculations. So I think you're all going to find that rather interesting too. And that tool is going to be very helpful because, you know, instead of you doing all this by hand in a calculator, you can do it in about 2 minutes using our online tool. So we'll cover that one as well. And then again, if we have time at the end, we'll cover those other topics I mentioned earlier. Okay, again, this is a standalone PV system, which means solar is the only charging source. We don't have a backup generator. We're not connected to the utility. We don't have wind power. This is it. Solar is the only source of energy to recharge this battery for the system. That's it. Okay, so we're going to jump into a couple of the considerations. One of the things is I know we've covered this quite a bit in my other webinars, but I want to bring it up again, shading. I'm just going to cover this briefly. If you want to get into more detail, we have tech notes available on that. You can see the link to that there. That also reminds me, we have several handouts as well. If you look at the panel on your screen, there's a little area that says handouts. We have some of those right there. Some of the ones that were important to review before this were the load calculations, as well as the IEEE 1562. We're going to get into that in more detail when we get into the sizing. But if you reviewed those before this, great. If not, that's okay. We're going to cover them generally, and if you want to cover them in more detail, you can grab those tech notes and read those later. But getting back to the shading, again, this is part of the considerations. You want to make certain you install the system in a place where the solar array will not be shaded. If you shade so much as a single cell, that entire solar module, or that entire string for that matter, anything wired in series with that solar module, the current output's going to go to 0. So that's it seems kind of, a lot of people always question me about that. Well, it's just shading just the corner of the solar array. Well, that's enough, again, to send that entire output to 0. We're actually going to cover that topic more in our EE 102 webinar coming up end of January. We're going to get into series parallel configurations and something called Kirchhoff's law when it refers to current, and it's going to describe why that happens. And this is one of the things, we're doing that webinar with regards to solar, and this is one of the things that actually applies to solar with regards to series strings. So we're going to get in that in more detail. If you're curious about it, if you don't care, then that's fine. Just realize that if you shade a single cell, that entire module goes to 0. So don't shade it at all. Some of the other things to consider when you're installing systems in North America, you want to set it for the maximum amount of sun you can get in the winter months, which is going to be a tilt angle of between 45 and 65 degrees. Typically, it's going to be latitude plus 15 degrees. And again, that shading is very important. Make certain that there's no shading whatsoever. And again, of course, that it's facing due south as well. I've had several troubleshooting calls recently about people having their solar arrays not working this time of the year, because this is the time of the year when you have the least sunlight, and of course their solar arrays weren't pointing south correctly. Plus or minus 10 degrees doesn't matter much, but when you're off by, say, 40 degrees, that does start to matter this time of the year. Okay, so now let's go through the basic steps to the sizing. First, you have to identify the sun hours at the site. Okay, and there are several places to get those data points and maps you can use. Okay, then you want to calculate or make certain assumptions about your system losses. Okay, and we're going to get into this more detail. Then you're going to need to calculate your load in amp hours per day. That's where that load calculation techno comes in. Okay, so you have to do that. And then we're going to get into, then you're going to take all those pieces of information from 1, 2, and 3, and you're going to use those to calculate the array size and the battery size. Let's go through a couple definitions first, though, that are going to be important to this conversation. One is ALR, or array to load ratio. We can hear that quite a bit. And that's covered in that IEEE document a little bit as well. And again, what this is the average daily amp hours produced by the solar array divided by the average daily amp hours per load. Basically what that means is that's the ratio of the energy produced by the solar array and the energy consumed by the load. You always want that number to be higher than 1, because if it's less than 1, that means the load's consuming more energy than the array can produce, and your system's not going to work. Okay, and we'll go in that in a little bit more detail when we start doing the calculations, and we'll start talking about that as well with regards to the IEEE document. But just so you understand what that means, again, we start talking about ALR, that's the ratio of how big the solar array is versus the load. Okay, and autonomy, that's the amount of time the battery can support the load. You'll also hear that term used with UPS systems. A little plug for that. Our next webinar coming up next month is UPS sizing. We'll talk about autonomy there again more. When working in UPS systems, you may be only using autonomy in terms of hours, say a 2-hour backup or 24-hour backup. And solar, we talk about it in terms of days. And again, the IEEE document talks about that. Generally, you want to have autonomy somewhere around 5 to 7 days, depending upon where you are in the country and the critical nature of the load. And again, we'll go into that in a little more detail. And the other thing is sulfation. I just bring that up because one of the things we're trying to do here is we're trying to size the system appropriately. If you undersize your solar system and you don't fully recharge your batteries, you will cause the battery to sulfate, which is a growth of lead crystals, the growth of lead sulfate crystals onto the positive and negative plates. So basically you get these sulfate crystals that will grow on the plates. This reduces the capacity of the battery and causes the battery to fail prematurely. So, and that sulfation is caused by the battery not getting back to fully charged. The reason it's not getting back to fully charged is there's not enough sunlight to do that, or basically because the load is too big for the system. So you'll hear sulfation used a little bit, so it's important to define what that is. The other thing is sun hours. You can hear that used quite a bit because that's what's used in the calculations. Okay, so sun hours is defined as the length of time in hours at a solar installation level of 1,000 watts per meter squared. Okay, that's needed to produce a daily solar radiation. basically, you can just think of that as that's what's used in the calculations, but it equates to 1,000 watts per meter squared, which is the ideal amount of sunlight that hits the solar array. It's also the amount of sunlight used in what they call STC standard test conditions, where they use to test modules. So module ratings are actually rated in 1,000 watts per meter squared, which is one of the reasons that we use sun hours to calculate it that way. And again, this is pretty much the amount of time per day you're going to get this ideal amount of sunlight. Obviously, in the morning you're going to get a little bit less. In the night, you're going to get a little bit more. But if you integrate that curve over the day, you're going to get a specific amount of sun hours. And again, that's going to change throughout the year, but you want to use the worst case, which for North America is always going to be the winter months, typically December or sometime between December, November, and January. A few general guidelines there. Generally, a place with low sunlight is going to be 1 to 2 sun hours a day. You can think of kind of either the Pacific Northwest or the Northeast, say like the Seattle area in the Northwest or the Boston area in the Northeast. In the middle area, you're going to have about 2 to 4 sun hours. That's going to be places across the middle of the United States. And then places with high solar resources are going to be between 4 and 6. Actually, 6 is rather high, to be honest. Generally, 5 is about the most I normally see in most of the southern U.S. And that's going to be more through the New Mexico, Arizona, Texas area. Even Florida doesn't get up to 5. Generally, Florida be in the high 4s, and that's because Florida has a lot of humidity, so they're going to have a lot of haze, and that haze reduces the amount of sunlight that can hit the solar array. Actually, the whole East Coast has humidity and haze issues that prevents it from being a high number. Okay, as I mentioned, here is an example of a solar map where it has, you can see it has a range. So each color has a range of about 1 sun hour, so you're going to go from 1 to 2 or 2 to 3. So you can see that on the map. Here's another variation on that, more zoomed in for the US. There are other sources of data as well. You can get some from NASA has data, NREL. There's a whole bunch of other databases out there you can use. There's a great one from Europe you can purchase by a company called MediaNorm. It's a wonderful one as well. There's a whole bunch of places to get data. What I would try to highlight, though, and this is the problem with the NASA data and some of the other online sites, is they're not using specific data points. They're using extrapolated data based upon satellite data or other or from real data from various weather stations. The problem with the extrapolated data is it can cause problems because it can't take into account weather patterns with regards to mountains and valleys and stuff like that. So we try to tell people to shy away from that. Sometimes you get into situations where you're on an island and out in the middle of nowhere, you don't have actual data, or some remote part of Canada or some other remote location where you cannot get anything within 100 miles of your site, then you're kind of forced to. But for most of the U.S., we've got some pretty good data. So I usually try to pick the nearest weather station that we have for that. That being said, my go-to source for that is the NREL database. It has been around for decades. I literally mean that, decades. I mean, they've been collecting data since 1960 on some of these sites. So that data is really accurate, which is one of the reasons I use it. It's also easy to find, easy to use. So that's what we recommend. And here's an example here. We're going to use this one, I think, in the calculations later on. We do examples of Alamosa, Colorado. And the thing I point out here is again, we're going to look at the, you'll notice that NREL has a whole bunch of different things. It's got various tilt angles. It's got 0 degrees, and then it's got 90 degrees. It's got stuff in between. Remember I mentioned that tilt angle is generally going to be a latitude plus 15. So that's the one you would want to use for this. And also note that if you go along there, you'll notice that the month with the lowest amount of solar data is going to be December. It's almost always December. And in this case, you'll notice, again, this is really good data for Alamosa, Colorado. It's pretty much kind of a high plain desert, and it's as high as 5.7. Again, I rarely see the 6, but I'll see the high 5s in certain locations of the U.S. This is a good one for those. So that's the number we would use and we'll use in these calculations. Okay, talking about methodology now. I've mentioned this IEEE document many times. IEEE 1562, and again, there's a handout tech note for that, or you can download it from our website. They'll go in that in more detail. You can also purchase a standard from IEEE. I would recommend that to you if you do want to do these calculations by hand or get more information on this method of sizing and how it works. There's a lot of good informative annexes in there that go into detail and some other stuff. It also has a worksheet to go through the calculations by hand. So if you would like to purchase that document from IEEE, you can. We're just summarizing that in both this webinar and on the tech note. The guide is titled Guide for Array and Battery Sizing in Standalone PV Systems. It uses the sun hour method. We've talked about sun hours quite a bit already. And the sizing is always based on the worst case solar installation, highest load consumption, and greatest system losses. And I want to point that out, highest load consumption, because that may not always be in the wintertime. Depending upon your load, you might have an air conditioner load, something like that, where it may be in the summer. Generally, though, it's going to be the winter, especially lighting loads. Lighting loads are always going to be worse in the winter. So I'd say 95, 99% of the time, winter is always worse, but there are a few occasions where it might be the summer or some other month, depending upon your load, if it's variable or not. Okay. Oh, just a quick reminder, I should have said this at the beginning. If you have any questions, please enter it in the question box in the panel, and we'll try to get those as we go, or certainly at the end. Okay. I will also want to highlight that the methodology, the idea is that the solar array is there to replace the amp hours in the battery that's been consumed by the load. So basically, the amp hours to the load is primarily being provided by the battery. Okay, and the array is there to recharge the battery. The array is not there to power the load directly. It is there to recharge the battery. So keep that in mind. And we're also talking about amp hours. We're not talking about watt hours. One of the things I see a lot is people that have been in the residential solar business for many years, which always works in watt hours because, in kilowatt hours specifically, because that is what your house consumes. That is what the utility is charging you. So when you're working on residential and utility, you're always thinking in kilowatt hours. But when you're working with batteries, batteries don't work in kilowatt hours. They're working in amp hours because that's the capacity of the battery. You see batteries specified in amp hours. So it's very important that when we're doing off-grid systems in general, and this is also true for UPS systems, anytime you're working with batteries, you always want to work in amp hours, not in watts, not in watt hours, but amp hours. So again, the idea is that the solar array is going to replace the amp hours consumed by the load. Okay, and then we need to oversize that, because if you were going back to what I was talking about, the rate of load ratio being 1.0 or 100%, that means then that there is no extra. There's no extra for losses. There's no extra to recharge the battery. And that's very important because you're not going to get 100% sunlight every day. You're going to get clouds some days. You might get a storm. You might get inclement weather. Who knows what. So you're not always going to have 100% solar every day. So you need to have extra to recharge the batteries when the sun does come back out. Okay, so that's why we recommend a rate of load ratio of about 1.2 to 1.4. And again, I'll go into that in more detail in a minute. Also, yes, you may also want to consider that, and I'll get into some more losses. We talk about the losses, that solar module power output does degrade over time. This is one of these interesting things about solar modules are they actually degrade in sunlight. The irony of that. So as soon as you put it out in sunlight, the module starts to degrade. The degradation is very low. It's between 0.5% and 1% per year, which is negligible if you're thinking 5 or 10 years down the road. But if you're thinking 20 years down the road, you're now looking at degradation to 10% to 20%, which now might be enough for your system no longer to work. So that's something you might want to consider either in additional rate of load ratio or perhaps in your system losses. Actually, usually I build those in the system losses personally. I usually add that as well as dust and other derates there. Okay, it's also very important that these calculations and your system sizing and performance is only as accurate as your load information and your solar insolation data. Again, I'll go back to the interpolated or extrapolated data is not nearly as accurate as having a nearby weather station. So I always try to use a weather station if I can. Again, it's always more accurate to do that We generally don't have an issue with accurate solar data. That's usually not going to be a problem for us unless we're in some weird remote part of the world. I think just any place in the U.S. we have good data. Like I said, we start getting into like Antarctica or something like that, that's a whole other situation. But here in the U.S., we're always pretty good. It's the accuracy of the load that's always the problem. It's very difficult for people to know what that is, but it's very important. Your system sizing really is only as good and as accurate as your load data and your solar insolation data. And as I was talking about sulfation before, if you're using a good battery and your system's properly designed and maintained, you should get about 5 to 8 years out of your batteries. If you're getting less than that, then check your system. There's something else going on. I mean, if your batteries are filling every 2 years, you've got a problem. Either your system has been undersized, which is kind of the point of this webinar and conversation today, or it could be your controller has been set incorrectly with incorrect set points. We've had other webinars on that where we talk about webinar types, controller types and things like that. So and also system troubleshooting. So I referred you to those for other troubleshooting things. But this one today is to talk about your system's undersized. Then you're going to have that problems. But again, if you have a well-designed, installed, and maintained system, you should be getting at least 5 to 8 years out of your batteries. So, one might think, well, we'll just go ahead and oversize the system and then we don't have to worry about that, which is also good, and we will oversize a little bit, definitely. But if you oversize too much, you're going to kind of waste money. Solar costs are very linear, so for every percentage you make it bigger, that's the percentage of cost extra you're going to have to it. Same thing for your load. Again, everything's very linear, so the bigger your load, if your load is 50 watts versus 100 watts, it's going to be twice the price of 100 watts than 50 watts generally. I mean, obviously you've got steps there, as you go from 1 module to 2 to 4, whatever, there's a sort of step, and same thing with the batteries. But eventually that will all kind of work out. So it's very important, again, to have this size correctly. You don't want to be oversized too much, but you certainly don't want to oversize. Okay, let's see. Oh, also, depending upon the nature of the load, you may want to oversize a little bit more. If you've got a very critical load where when your load is down, it's going to cost you money. I mean, I hear stuff like, $1,000 per hour for some, oil and gas pipelines for the flow. It's worth spending a little extra money to oversize your system. So keep that in mind as well, that depending upon the critical nature, spending a little extra money to oversize it may not be a bad thing. Okay, let's see. I talked about system losses just a little bit. They're going to be used as a percentage of the system load generally. I mentioned dust. You may want to have array degradation in there I mentioned earlier. Battery inefficiencies definitely, and other parasitic losses. You can have controller losses, inverters, although sometimes I will build the inverter losses into part of the load calculations instead of putting it into the system losses. But another one is voltage drop in there too. You can have voltage drop in there. So there's all kinds of losses you can put in there. Typically it's between 10 to 20% is pretty typical what we use, and that's usually pretty good. If you couple that with a decent array to load ratio, you're going to have a pretty reliable system. Okay, so let's go into the load calculations here quickly. So, and again, referring back to that tech note on understanding your loads, if you want to go into that in a little more detail. So again, we mentioned this before, we want to use the average daily load amp hours per day. Okay, and if your load, it can be very simple. If your load is in amps, great, just multiply it by 24, now you have 24 hours a day. If your load is in watts, then you divide that by your nominal system voltage and then multiply that by 24 volts to get amp hours per day. And for those of you who caught my webinar on EE 101, this gets back to that units matters types of thing. Again, we have amps times hours equals amp hours, and if it's hours per day, in the case of 24 hours per day, that's how you get amp hours per day. So it goes back to, again, units always matter. So let's go with, we're going to use these examples throughout this exercise. So example 1 is going to be a 0.75 amp continuous load at 24 volts. So again, it's as simple as multiplying the current, 0.75 amps, times 24 hours a day, and we're going to get 18 amp hours a day. Again, that's at 24 volts. That is not the same as at 12 volts. So keep that in mind, that amp hours is a specific voltage. We can also do this in watts, as I said. So we got 15 watts continuous at 12 volts. So you're going to take the watts divided by the nominal voltage, then multiply that by 24 hours. So it's going to give us, in this case, 30 amp hours per day. And again, that's going to be at 12 volts. Okay, some of the other things to consider in your calculations, I mentioned inefficiencies. For inverters, you can also have DC-DC converters in there. So when you're working with loads that are not a system voltage, you need to include the losses of the converter equipment in there. Again, either the inverter or DC-DC converter. Intermittent loads should be averaged. Sometimes you might have some type of pump or valve or actuator or something like that, where it may be operating for, I don't know, 5 minutes every hour, something like that. That should just be averaged for that day. Future expansion should also be considered. That's big in telecom. I know telecommunications are always trying to, thinking about it. Hey, we only have this much coverage now, but as activity picks up, we may need to put an additional 30% for additional coverage and for additional usage of the cell tower type of thing. There's also kind of again, you may want to also add a little extra in there for uncertainty in the runtime. Sometimes if you're not positive how much it will run, sometimes you might have radios that poll at variable rates. So you may want to try to use worst case in there always. Better to do the calculations based upon worst case than what you think the average might be, and then have it increase and have your system not work right anymore. Also consider inrush current when working with some of the other loads, AC loads specifically. A lot of devices on startup are going to have a high inrush. Generally, you don't have to worry about that in the system sizing too much, but that might happen when it comes. That might come and you might have to take that into account when working with converter devices like your inverter or DC-DC. I also want to highlight with the inverters specifically that this is something a lot of people forget, is inverters, not only is there an efficiency issue, when the inverters are not being used, they have a loss to them. Just to have them be ready to use, the conversion device inside, your transformers and inductors and capacitors, they're all charged up, and they're wasting energy while being charged. And that can be as little as 3 to 4 watts or as high as 30 watts or more, depending upon the size of the inverter. And if you're working with a small load of, say, 8 watts, and your inverter is wasting 3 to 4 watts, and by the way, that's how much the smallest inverters are consuming, you may need to add in the tare losses of your inverter basically in as a actual load in your calculation. So imagine that, you got an 8-watt load, but we have to add an additional 3 or 4 watts just for the inverter. And as bizarre as that sounds, that is true. I've seen a lot of sites go down because people don't think about that. So keep in mind that some of your conversion devices or other things, like if you have in some cases I've seen really inefficient charge controllers be a load. So think about all the components in your system. Some of those components may not just be in your system losses, but they also may be a load on their own almost. So you can almost include those losses as an actual load.
Hey Rob, I have a real quick request. Could you just go back one slide to the calculations really quick so we can just look at that for a moment? Somebody just wanted to see that really fast again.
This one?
Yep, I don't think they had any specific questions. I just wanted to bring it up for a few seconds so that they could see it again. And of course, this will be recorded as well and posted, so everybody can go back and review this as well. Okay, that's all, Rob. Thanks.
No, thanks for the reminder on that, Errol. I forgot to say that at the start. Okay, so let's dive into the array sizing. So again, we're going to use as accurate solar and load data as possible. We're going to account for system losses we just talked about, and we're going to do this per IEEE 1562. And Section 9 of that, and again, I refer you back to the tech note on that one, states that for non-critical loads, an area of high solar insolation. That's the key here. It's not just non-critical loads, but also high solar insolation. You can use a ALR, or rated load ratio, of about 1.1 to 1.2. And when I mean high solar insolation, I mean, Arizona, Texas, New Mexico type of thing. I'm not talking about the middle of the U.S. I'm talking about the southern regions. Okay, so for critical loads and areas of low solar insolation, we recommend, the guide recommends a rate-to-load ratio of 1.3 to 1.4, or even higher if you want to. It does not hurt to go higher. And I will say this, that document was written 10 years ago now. It was written in 2007. We're now 2017. And when it was written, solar was rather expensive. I mean, I think solar was 2, 3, or 4 times as expensive for a solar module than it is today. The rest of the cost of the systems are about the same. Cost of the batteries have gone up a little bit and a few other things, some of the other balance of systems items, but the solar module itself has dropped dramatically. So when this was written, they were just trying to write it to be as conservative with the solar array without oversizing it too much to make it too expensive. But with solar module cost being so low now, we have been erring on the side of let's just make it a little bit bigger. If it's a question, let's just add a little more solar to it. So we actually don't really even use the 1.1 much anymore. Generally, we'll use the 1.2 or higher, just because solar has gotten so inexpensive now versus 10 years ago when this document was written. So just also keep that in mind, something to think about. Okay, so here's the formula for that. And so again, it's going to be the load in amp hours per day times 1 plus the system losses, which is in a percentage, times the rate-to-load ratio. And then we're going to divide that by the sun hours per day times the current. And this is the max power current, not the peak, not the short circuit current, but the peak power or max power current of the solar module. So you also have to select your solar module in advance, and that's one of the other problems with this is I have to decide, and you may not know whether you need a 40-watt module or an 80-watt module when you start this process, so you may have to go back and do it again. You may have to go, you know what, my 80-watt has been oversized and I can go use a 40-watt instead. And we're actually going to show you an example of that happened by accident. We were updating this this webinar of how that was one of the things we discovered. But keep that in mind that you have to actually pick your solar module in advance as well and see how well it's going to work. Now for the bigger systems, that's not a problem because you just go ahead and use the biggest module. But if you're working on a smaller system, you don't know whether you need a 40-watt or 60-watt or 80-watt in advance. You may have to go through these calculations multiple times to figure out which solar module might work best. And again, going back to how the units matter, you'll notice that the hours per day times the amps in the modules gives you amp hours per day. So you're going to divide the load amp hours per day literally by the amp hours per day and the formula underneath. So so you're going to notice that the amp hours and the load are going to be divided by all of this, and next thing you're left with a number. There are no units left because this is number of modules. There's no amps, watts, or volts left. It's just a literal number. So again, just to highlight some of those things, the rate-to-load ratio is something you're going to have to consider using based upon the IEEE document. And again, we've already mentioned that module selection. Let's see. Okay, I think we've already covered all of that. Okay, so going back to that example one we mentioned earlier, where we came up with 18 amp hours per day for the load. Okay, we are going to we're going to go ahead and use a system loss of 20% just for discussion purposes here. And we're going to select a rate-to-load ratio of 1.3. And we're going to use the sun hour of 2.5, and I think that was the one, I forgot which site we selected. But we're going to use the sun hours of 2.5, and we're going to use a module current of 6 amps, and that's basically the current from a 110-watt module. Okay, and if you multiply the 18 times basically 1.2 times the 1.3, and you divide that by the 2.5 times the 6 amps, you're going to get 1.9. Now you can't get 0.9 of a module, so you obviously just round up to the nearest number. And actually, this isn't the number of solar modules you need; it's the number of strings. If it was a 12-volt module and a 24-volt system, you'd have to have 2 of those in series. Then you need 2 strings that would be 2 by 2 in series by 2 in parallel, which would give you 4 total. In this case, because it's a 12-volt module and a 12-volt system, it's just 2 strings or 2 modules in this case. Okay, so battery autonomy, it's a little bit easier. But going back to the IEEE document again, and that critical versus non-critical loads and high solar insolation versus low solar insolation, we're going to do the same thing for the battery. So for non-critical loads and high solar insolation, IEEE recommends a battery autonomy of 5 to 7 days. And for critical loads and areas of low solar insolation, 7 to 14 days. I've actually even seen higher than 14 days for some places. I've seen people use some numbers as high as 21 days. I also want to reiterate that, that does not take into account any degradation of the battery due to either aging or due to temperature, especially the temperature. Temperature can have a huge effect on a battery, and if you're right around freezing, say 0 degrees Celsius, your battery capacity can be reduced by to 80 or 85%. So if you're using a 100 amp hour battery, any place that's near freezing, especially in the wintertime, which is when you have the least amount of sunlight anyway, your battery really may not be 100 amp hours anymore. It may only be 80 amp hours, as an example. So this does not take that into account. If we have some more time at the end of this presentation, we'll get into that in more detail. If not, you're welcome to also look on our SunWize's website. Under Learning, you'll find there's a tech note on temperature effects on batteries. We'll go into that in more detail. Okay, so the battery calculations are similar and pretty simple, actually. It's just the load amp hours per day again times the battery autonomy, and again, that's in days, okay, and you divide that by the maximum battery depth of discharge that you would like to get. Now, normally with a lead acid battery, if you discharge a battery completely, you can't use it again. So generally, you only want to discharge a battery to about 80%. So you only want to use 80% of the rated capacity, not 100. And that's for the good quality batteries. For really low quality batteries in the old days when they didn't have solar batteries available and they had not developed the technology they have now for these batteries with the alloys of the plates and stuff like that, when they were using lousy batteries, they used to actually use the depth of discharge of 50% because those batteries could not cycle well. So today's solar batteries are much better, technology is better, and you can cycle these to 80% depth of discharge pretty well, so that's what we generally use. But again, you may want to look at your battery and consider using maybe something not as deep if it's not as good a quality, but you never want to use 100%. Now, this is with lead acid batteries. A lot of people like to use NiCad batteries, which are a little bit more robust but also more expensive, because they can discharge them to 100% and the battery won't die. You can do that repeatedly. But the problem is that what people don't take into account is that, yes, you can discharge a battery 100%, but to do so, the voltage goes to 0, and your load's not going to work at 0 volts. So even with a nickel-cadmium battery, you can really only extract 80 or 90% of the battery, because at that point, the voltage collapses so far, the load can no longer operate. So like I said, generally I usually defer to 80% on that one, unless for some reason you want to use a higher number like 50. And that will give you your battery capacity. So again, if you go back to the units, days divided by days is going to give you amp hours, and the depth of discharge is in percent, so that's just a number, there's no units there. Okay, I think I already covered that. So going back to the example again, we have the 18 amp hours per day for the load. We want to use a 7-day autonomy, so that's the 18 times the 7, and we're going to divide that by 80%. That's going to give us 157.5 amp hours per day. Now, I want to reiterate, that's the minimum size you want. You're not going to be able to find a battery that's 157 amp hours. You just can't. So you may have to go to a slightly bigger battery. So keep that in mind, that you want to try to find the nearest battery to that, or you can use multiples. Let's say you've got in stock, you got a good deal on a pallet full of, group 27 100 amp hour batteries. You could just use 2 of those. It means you might have a 10-day battery instead of a 7-day. That's good too. So you just want to try to use the nearest size you can. Just keep that in mind. If you want to use a single battery, you could use a group 4D, which is around 200 to 210 amp hours. Again, it'll be oversized, but that's what you have available. Okay. Just to reiterate again, we're always going to try to use solar data that's as accurate as possible. I highly recommend the NREL data, which is from the Red Book. Again, we're going to use the latitude plus 15 for this location. You can, again, it's going to be we're going to use the December number, and that's going to be 3.8 sun hours a day for this location. So going back to going into another example, we're going to use a load of 15 watts at 12 volts continuous. And we're going to use the location of Huntsville, Alabama. Oh, that's where that was. I'm sorry, that was for Huntsville, Alabama. And that's going to be 3.8. Okay, if you want to use a map, you might use 3.5. Now notice that's a little bit less. It's okay to go a little bit less. It's going to make your system a little bit bigger. That's okay. If you oversize a little bit, that's better than undersize your system. Again, you don't ever want to undersize. That's going to cause your batteries to sulfate, and they're going to die prematurely. So always better to oversize. It's going to cost you a little bit more money, but you're going to get better reliability, better performance, and you're going to extend the life of your components and system. So you may spend a little more money now up front, but it's going to save you money later, because if you undersize and cycle your batteries too much and replace them prematurely, that's going to get expensive. The batteries have gotten so expensive now, and the cost of the solar modules have gotten so inexpensive that the batteries are now generally about 40% of the cost of systems. They're somewhere around there. So imagine, basically wasting 40% of your cost of your system because you didn't want to spend the extra 5% on the solar array. So just keep that in mind, that really adding extra solar to make your system more reliable is a good thing to do nowadays. It'll save you money later to spend a little bit more upfront. Okay, so going through the 5 basic steps, we've got the sun hours identified, that's 3.5. We're going to assume losses of 10% in this case. Okay, so now we need to calculate the load in amp hours per day, and then we're going to size the array and the battery. So if we take those 15 watts at 12 volts, so we divide that and then multiply by 24 hours, we need 30 amp hours per day. Okay, now let's go into the array calculations. We're going to take those 30 amp hours times basically 1.1, that's the 1 plus the 10% losses. Multiply that by the 1.2, it's a non-critical load. Okay, then we divide that by 3.5, which is the sun hours, and we're going to use, in this case, 7.8 amps because we're going to use a 140 watt module. And again, remember, that's the peak current rating, not the short circuit current. That's very important to use the peak, not the short circuit. And also, we're also using STC ratings, by the way, too. We're not going to use NOCT. Some modules have an NOCT rating. We're not going to use those. We're going to use the STC. And again, it's the peak or max power rating. So once you're done with all those calculations, it's going to come out to 240 watt modules, or 2 strings again, because it's a 12 volt system, it's the number of modules. But if you had a 24 volt system, it would be double that, because you'd have 2 modules in series and 2 in parallel. And again, you round up. Looking at this, if you had a bigger module that you might be able to use 1, I mean, if you had a 190 watt, maybe you could get away with 1 instead of using 2 of the 140s. Or if you have maybe a smaller module, maybe you could use 2 100s instead of 2 140s. So something else to think about too. You can go back and redo the calculations to get a little closer to maybe like a number of either like 0.9 or 1.9, depending upon how many you want to put in parallel. And we'll do an example of that in a little bit too as well, going back and redoing those calculations. So now going through the battery calculations, you got that 30 amp hours per day times 5 days. We're going to go ahead and use 5 days because, again, it's a non-critical load. And we're going to use an 8% depth of discharge I mentioned earlier. You do all those calculations out, and you're going to get 187.5. As I mentioned earlier, you can bump it up to the nearest size battery you got. You can use 2 of the Group 27s. That's going to give you 200 amp hours roughly. Or you can use 1 of the 4Ds. That'll give you 210 amp hours. Either one will work. Just depends on which one you want to use. Okay, so let's review those results again using the 5 basic steps. We've identified the sun hours. That was 3.5. We assumed the losses of 10%. We calculated the load to be 30 amp hours per day. We ended up sizing the solar array as 2 of the 140 watt modules. That's 280 watts total. And then we sized the battery bank for a minimum of 187.5 amp hours. Now this is one area I want to bring up, our online sizing tool. If you go to sunwize.com, in the top header, you'll see a tab that says build your system. you would do a drop down to New System Design Tool. Then you would select Build a Solar System using our PRE Design Tool. The other option is we also have tables and kits that you can do, and you can also drop down to the Complete Solar Systems and pick up the Power Ready Express kitted systems, and that's going to give you a spec sheet where you can go ahead and do that based upon the map and some charts. So that's an option as well. Although I would prefer, personally, I would prefer to use the online sizing tool to get a little more accurate. I also want to highlight here, right next to the Build System tab is the Learning tab, where you can find all of the stuff I'm talking about. You can find the tech notes, recorded webinars, like this one will be up there later on today, and other great information like that to help educate yourself in the solar industry, as well as UPS and other off-grid solar solutions. So if we actually go ahead and ran this system through our design tool using those numbers, using 3.5 sun hours a day, using the system loss 10%, with the 30 amp hours per day, it's going to kick out a standard system for you, our part number 270314, but it's going to be a little bit bigger. It's going to be a 300 watt solar array instead of 240 watt, and it's going to be 216 amp hours instead of, say, 200 or 210. So it's a little bit bigger, but you didn't have to spend time calculating it, and you've actually got the part number for a system that already exists. So the neat thing about, and here it is, here's the part number for you. So what that means is that you can actually, in a matter of 2 minutes, you can get yourself an actual cost for something. So if a customer calls you up with a load, based upon that information, you can very quickly give them a quote of how much it's going to cost for a solar system to support that load. So instead of you having to go through this process of perhaps calling your account manager or having them do the calculations for you and getting back to you with a quote, or instead of going through the calculations yourself and spending all that time, you can pretty quickly get a pretty accurate budgetary number for that. So I think it's a pretty powerful tool, and it's something to keep in mind. And some of you are probably saying, so why did I sit through this webinar? And actually, if you want to know more about that online design tool, we actually have an entire webinar just dedicated to that. So if you'd like to try to learn more about that and go through examples, actually Errol did that one for us. That's also on our website under the training tool, under the training tab, as I mentioned just a minute ago. So that's kind of a neat exercise. So again, to try to highlight that, you can do it by hand, which is going to take you a whole lot more than 2 minutes, or wait for your account manager to get back to you with a quote. Or you can use our online sizing tool. In about 2 minutes, you're going to get your answer. The difference here is your array might be oversized by 7%, your batteries by 15, but again, you're conservatively sized. Better to have it be a little bit bigger and operate than to have it be a little bit too small. So that was kind of a neat example. Example 2 gets even more interesting. We're going to put some variable loads in here now and at different voltages. So we're going to go use a 15 watt load at 24 volts, but it only operates for 4 hours a day. Then we're going to throw in a 5 watt load for 12 volts for 23 hours, and then a 1 amp for 12 hours. And a lot of times you'll see radios like that. You'll see a radio that's going to operate at a higher wattage or current for like an hour on transmit. And then you're going to see it's going to be in standby mode for the rest of the time at 23. Excuse me. So that's a pretty common type of load to see sometimes, especially when working with radios. We're going to select Boulder, Colorado for our location, and we're going to use a system voltage of 12 volts because our biggest load is at that voltage. Generally, if you have multiple voltage loads, you're going to have to use a conversion device that's going to have losses to it. So you generally want to minimize those losses. So you want to use the system voltage that correlates with the biggest load you have. In this case, that 1 amp at 12 volts is going to be the biggest load combined with the 5 watts. That's what we're going to go with. Okay, and because we have, like I said, because we have Boulder, we actually have an NREL data point for that. That's going to be at 4.9 sun hours per day. Or in this case, if you want to, we can also use 5.0 from the map. Okay, so we've identified the sun hours at 5.0. Again, we're going to use a losses at 10%, so I need to calculate the amp hours per day, do the array sizing, and the battery calculations. So this is going to get a little trickier. So we're going to have to take each load individually. So let's take the 15 watts. We're going to divide that by 80%. That is our conversion losses. Okay, so that's the losses from the DC-DC converter. They're going to divide that by 12 volts. That's the nominal system voltage. They're going to multiply that by 4 hours. And if you got a calculator, that comes out to 6.3 amp hours a day at 12 volts. Okay, the other one is not quite as complicated. We're going to take the 5 watts divided by the 12 volts, multiply by 23 hours, because that's how long that's going to operate. That's going to give us 9.6 amp hours per day, 12 volts. Load 3 is the easiest. It's just 1 times 1, which gives us 1 amp hours per day. Don't need a calculator for that at 12 volts. Now, if we add those all up, 6.3 plus 9.6 plus 1, we're going to get 16.9 amp hours per day. So now we have our load. So we take our 16.9 amp hours per day, multiply by 1.1 for our 1 plus our system losses, times 1.2. It's a non-critical load. And we're going to divide that by 5, the sun hours per day, times 6 amps. That comes from the 110 watt module. And that's going to give us 0.74. Now, again, you have to bump that up to, obviously you can't do 0.74 module. So it's one module. So it's one module. It's a 110 watt module. That's it. But we've left, if we're going to cover this in a minute, remember I said earlier about, hey, that's fine, but you might be able to use a smaller one, so you have to go back and redo the calcs. We're going to find something out that's kind of interesting here. So again, in this case, a smaller module is possible. We're going to come back to that, so keep that in mind. Also keep in mind, we're going to go ahead and use our online tool to see what it would spit out for an answer. But let's jump over to the battery calculations here first before we do that. Take the 16.9 for 5 days autonomy. Again, it's a non-critical load. Divide by 8% depth of discharge, and we come out with 105.6 amp hours. Again, that's the minimum size. In this case, we can get a really close battery. Group 30 batteries are about 108 to 110 amp hours. So right there, we're pretty much right about at the 5 days with the group 30 or 31 batteries. So that works out really well. So to summarize that, we've got 5 sun hours for the site, system losses assumed at 10%, calculated the load to be 16.9 amp hours a day, using a 110 watt module. We only needed one of those, and the battery has to be a minimum of 105.6 amp hours. But what if we decide to go ahead and use our online sizing tool? This actually gave us a standard system number of part number 270305. Again, we used the 5 sun hours a day. We went ahead and assumed the 10% losses. We didn't have to do the load calcs this time because our online tool does the load calcs for you, by the way. And again, this is a pretty tricky one, so that was not fun. So it would have done the calcs for us, and it would have still given us 60.9 amp hours per day. And in this case, it actually realized that a smaller module would work, and it used an 80 watt module for us instead of 110, and it used the same battery we would have used, which is 108 amp hour group 30 battery. So if we go back and think about that, by hand, we used a array that ended up being 27% too big, and the batteries are right about the same. So again, this also gets back to if you come across a huge number that's not near, that is a lot less than a whole number, you may want to think about going back and resizing your array to get something closer to that. Otherwise, you might be wasting money. This is a good example of that. You're spending an extra 30 watts for a module. Essentially, you're buying a 110 instead of an 80. Without going back and doing an exercise. Or again, if you just use our online tool, it'll spit out the system for you. You're good to go. So that's kind of an interesting exercise. And we can go back. If you want to go back and redo it, everything's the same other than a 4.3 amps for the 80 watt instead of the 6 amps before. And actually, it gives you 1.03. Technically, you're supposed to bump that up to a 2, but to be honest, if you rounded it off, it's really 1.0, so that's close enough. Okay. Again, just want to highlight a few more things. If you're in an area with a critical load or poor solar insulation, you want to use that rated load of 1.3 to 1.4 instead of the 1.1 to 1.2. And again, the autonomy of 7.9 days, 7 to 9 days instead of 5 to 7. And again, be conservative. Better to have it oversized than undersized. But again, you don't want to oversize too much because you don't want to pay twice as much as you need to. Okay, and again, always go through the same process. Nothing else changes. I think you guys, after all those examples and calculations, I think you got the idea on that one. Okay, and again, we've got all these other tech notes and other things. I think we only have about 5 minutes left, so I think we are unfortunately out of time, so I'm not going to cover these topics today. But again, there are all these good tech notes on those if you want to go follow up on those at your leisure. So let me skip through all of those and get to, again, just to highlight our design tool. I think I showed you what it was online. Also, there's the webinar for that as well if you want to go through that also before you go ahead and try the tool. But it's pretty straightforward, very self-explanatory, and I think we might even have a PDF on that now for the instructions. I think, Errol, was that included in the handouts? The PDF instructions for that? For the online sizing tool?
Yes, they are.
Okay.
I highly recommend folks grab that because we haven't posted that on our website yet. We will, but that's a fresh new document, so highly encourage folks to take a look at that.
So see that, by joining our webinar today, you have an exclusive. Not even on our website yet. Okay, I think we have about 5 minutes left for questions. I know I apologize for going through everything quickly, but again, there's a lot of material to cover, and we try to do our best to get through everything in this hour as best we can. So I'm certain there are some questions. So Errol, who do we have first?
Thanks, Rob. I've had one question so far that I addressed generally. I'll go ahead and repeat it here just for clarity. Somebody mentioned that the inverter losses are close to 10%, and then there are also the battery losses, so why are our total system losses only 10%? I mentioned that in the example that we did, I actually don't know if you want to go back to the slide in question, we calculated the inverter losses through the load calculation. What that means is that inverter loss is therefore in addition to the 10% general system losses that we have. Yeah, it was that slide that you just went.
Yeah, is this one? Yeah, we didn't. In this case, in this case, we didn't use an inverter. We used a DC converter, but the same principle applies. And I would say most inverters have an efficiency of around 90%. Some of the bad ones might be as little as 87. Some of the better ones may be up in the low 90s, like 92, 93. But on average, are right around 90. DC-DC converters can range from 80% up into 90%. It's rare to find one bigger than 90, but they're somewhere in that range, and that's quite a that's quite a bit of variation there. So definitely check the spec sheet. And sometimes it's worth spending a little bit more money for a more efficient DC-DC converter because you'll save it on your system sizing here. Because you can make your system, say, 10% smaller, so that might save you some money. Even though the converter might be more money, the system might be a little smaller, so you can save the money there. But yeah, what we do is we've actually, to get back to the question though, we've used the losses of the conversion equipment, either the inverter or the DC-DC converter, whatever it is, in our calculations, as we have here an example. One, the 15-watt load was at 24 volts, not 12. So we took that 15 watts at 24 and divided it by the converter efficiency of 80%. And then by the nominal system voltage of 12 volts. Now, again, let's say it was a 15-watt AC load. Let's say it was 15 watts at 120 volts AC. We would do the same thing. We just divide that wattage by 90% for the inverter efficiency, and then divide it by our nominal system voltage of 12 volts. So generally, we
Rob,
don't.
I just wanted to mention one extra thing, actually, while we're on that topic, which I think is a great opportunity, is that if this was an inverter, say a 15-watt inverter with, say, a 90% efficiency, we would do that conversion, 15 watts divided by 90%, just like we're doing in that load 1 example, and then we would also likely add a load 4, and that load 4 would just be the standby tear loss of that inverter, which could be, say, 2 to 5 watts. Right, Rob?
Correct. In that case, we most likely would, because it's a small load and that tear loss is rather large versus the small load. That's correct. Yep. So that's how we would.
That's a good opportunity.
That's actually a good question on the inverter, though, and how would you handle that? And we did all DC here, but if you have an AC load, the calculations work the same way. And let's say you had an AC load of 1 amp at 120 volts. It's the same thing. You would then multiply. You would actually convert those to watts. So you take the 1 amp times 120 volts AC. That would give you 120 watts. Then you divide that by your 90% loss, your inefficiency. Then you would divide that by your system voltage. If I was working with 120 watts, though, I probably wouldn't use a 12-volt system. I'd probably go to a 24-volt system or even 48. Probably go to a slightly higher voltage to keep my currents a little bit less. But that is a good question, though, because he didn't really cover that, so I'm glad somebody brought up an AC question. But generally, I usually include my inefficiencies of my conversion equipment in my load calculations, and I usually use the system losses for things like voltage drop, battery inefficiencies, and perhaps even your controller losses.
All right, Rob, I don't have any other questions. I guess we'll give people a few more seconds to get any in if they have them, but I think the presentation was very clear and concise and apparently pretty comprehensive.
Okay, and while we got a few more minutes, just a few more, so we give people a few more seconds. Just want to plug our next few webinars again. Our webinar coming up next month is going to be on UPS sizing, so it'll be something similar to this, but with UPS systems. So if you do a lot of battery backup, I'd recommend you catching that one. And then later on in January is going to be our EE102, and I highly recommend you go, if you have not seen our EE101 webinar, I would go and view that recorded one first, because we're going to build on that for EE102. So if you didn't do the EE101, I highly recommend that if you want to do the EE102, because again, you might get a little lost with some of the stuff, because we're going to do a quick review, but we're going to get into detail on some of those things. And that is going to be, I'm going to try to keep it as simple as I can and try to, again, just like the EE101, we're going to make sure that these electrical engineering theories apply to solar and how does it apply to solar. So I'm going to definitely do that, but it's going to go a little bit more in depth in some of these things. Like I'm going to bring up Kirchhoff's laws that apply to electricity and things like that. So we're going to go a little bit more in depth in some of those things. So it's going to get a bit detailed, but it'll be interesting if you're curious about, why does a solar module go to 0 amps when you shade one cell. It's going to go into things like that. So it's going to go into the principles behind series parallel connections and stuff like that. And it can be very helpful, again, to understand these things when working on these systems. So I highly recommend that one as well. And always just keep checking our website for all the latest webinars coming up and for any recorded ones you might have already missed. So okay, if there are no other questions, then I guess we will conclude our webinar for today. Thank you everybody for joining, and I look forward to seeing you all again on our next webinar. Thank you.
Thanks, Rob.